If you draw a simple closed loop, telling the inside from the outside feels obvious. But when that path tangles and crosses itself, how does a GPU decide which regions to fill with color? Straight rays shot through the shape can easily get confused by the self-crossing lines. By the end, you will see how a simple rotating tether turns this spatial visual puzzle into an elegant foolproof test. To see where the problem begins, let us start with the simplest possible shape, a smooth, closed circle. Suppose we place a query point inside the circle, shown as a bright golden dot. If we cast a straight ray from this point all to infinity, that ray must pierce the boundary to get outside. For any point inside, a straight ray crosses the turquoise line exactly once. An odd number of boundary crossings tells us the point is inside. If the point were outside, a ray would cross 0 times or twice. On simple loops, counting boundary crossings works like magic. Now, you might expect this simple rule to hold for any shape, but watch what happens when a path tangles and crosses itself. Take a 5-pointed star drawn as one continuous vector curve. If we place our golden query point right in the central core and cast a ray to the right, that ray pierces the neon turquoise path twice. Under our simple boundary rule, 2 crossings mean an even count, which labels the point as outside. The algorithm leaves the very center of the star completely unfilled and hollow. Our intuitive test has already broken down. And here's the deeper issue for a GPU calculating thousands of pixels in parallel. You might hope to fix this by picking a different ray direction, but straight rays are fundamentally fragile. If our ray happens to pass through a crossing vertex or graze an edge tangentially, the crossing count becomes wildly unstable. A tiny shift in direction can cause the count to jump from 2 to 1 without the point moving at all. A GPU cannot rely on an inside-outside test that changes its mind based on an arbitrary ray direction. Remember this instability. It will matter later. So, counting boundary walls gives us a test that is easily confused by self-intersection and tripped up by geometry. We need a completely different perspective. Instead of shooting rays out to infinity, imagine keeping our eyes entirely on the shape itself. Suppose we attach a flexible golden tether from our query point to a tracer moving along the boundary path. As that tracer completes a full circuit along the turquoise curve, the tether continuously sweeps through space. Loosely speaking, tracking this continuous rotation gives us a test that never gets confused by crossing lines. Watch what happens to that golden tether as our tracer completes one full circuit around the circle. As the white dot glides counterclockwise along the turquoise path, the tether sweeps through space like the hand of a clock. Notice that it does not just point in different directions. It smoothly completes one full turn, sweeping out exactly 360 degrees. Now, you might wonder if this angle tracking is just a fancy way of saying we are inside. But watch what happens when we move our golden query point outside the shape. Suppose we shift our golden query point outside the turquoise loop and run the exact same experiment. As the tracer dot begins its journey along the top edge, the golden tether pivots counterclockwise, sweeping out positive angle. But as the tracer continues around the bottom edge back toward the start, the tether is forced to reverse its rotation, pivoting clockwise. The angle swept during the second half of the journey undoes the angle from the first half. By the time the tracer completes its circuit, the net accumulated angle drops back to exactly 0 degrees. This simple contrast reveals the heart of our new approach. Raycasting tried to judge inside from outside by counting abrupt wall crossings, which broke down uncomplicated geometry. The tether perspective replaces that static count with a continuous journey. By anchoring a line to a tracer along the boundary, we convert a tricky spatial enclosure question into tracking total accumulated rotation angle. Whether a point is enclosed depends not on straight lines, but on whether the tether wraps around it. Next, we will see how this angle tracker handles paths that cross themselves. Now that we see how rotation measures enclosure, a crucial question arises. What happens when a path changes direction or crosses over itself? To find out, consider a path shaped like a figure 8. As our tracer dot glides along this turquoise curve, notice how its orientation shifts. The tracer orbits counterclockwise around the left lobe, but clockwise around the right lobe. To track this, we give rotation a sign. Sweeping counterclockwise adds positive angle, accumulating up to positive 360 degrees. Sweeping clockwise does the exact opposite, accumulating negative angle down to negative 360 degrees. Watch how this signed angle handles query points in different regions of our figure 8. When we place our golden query point inside the left lobe, the tether completes one full counterclockwise sweep. The net accumulated angle is positive 360 degrees or positive 1 turn. If we move the query point into the right lobe, the tracer orbits in reverse relative to our point. The tether now completes a full clockwise sweep, giving negative 360 degrees or negative 1 turn. And if the point sits outside both lobes, the positive and negative rotations cancel out completely to 0 turns. Now we can return to the 5-pointed star that broke our simple ray casting rule. Remember how straight rays cross 2 boundary lines at the central core, leaving the star center unfilled? Let us see what the rotating tether discovers. As the tracer dot traces all 5 points of the turquoise star, the tether wraps around our central query point not once, but twice in the same counterclockwise direction. The accumulated angle reaches positive 720 degrees, which simplifies to positive 2 full turns. Because this net count is non-zero, the GPU knows without any ambiguity that the center is enclosed. This integer count is called the winding number of the point. Dividing the total accumulated angle by 360 degrees distills any continuous journey down to a single whole number. Notice the power of this idea. Opposite rotations cancel each other out, while repeated loops add together. Every region in space receives a clear invariant winding number, whether it is 0, positive 1, or positive 2. Now, you might notice something striking. As long as our query point stays within an open region, its winding number never changes. Next, we will explore what happens the exact moment that point crosses a boundary line. Let us see what happens when we move our query point around. Suppose we drag the golden dot around inside the outer region. As long as the point remains in open space without crossing any turquoise lines, the total rotation of our tether stays exactly the same. If you nudge the point slightly to the left, the tether swings a bit differently at each instant. But those small shifts compensate for each other over the full loop. The winding number stays locked at 0. Within any connected region of open space, the winding number is completely constant. But what happens the moment our query point crosses a line? Watch closely as we drag the golden dot from the outside region directly across a turquoise boundary line into the single loop region. As the point steps over the path, the tether gets caught on the boundary wall. To clear the line and stay attached to the moving tracer, the tether is forced to whip around by a full 360 degrees. Crossing the path causes the accumulated angle to instantly jump by 1 full turn, changing our winding number from 0 to positive 1. The direction of the jump depends entirely on which way the boundary path is traveling relative to our movement. If the path passes from right to left across our line of motion, crossing it adds positive 1 to our count. If we cross a line moving in the opposite direction, the tether whips in reverse, subtracting 1 turn. Notice what this means. No matter how tangled the shape becomes, crossing a single path segment always changes the winding number by an exact integer jump of +1 or -1. Here's the beautiful connection that brings us full circle back to ray casting. To find the winding number of any point, we do not actually need to track a rotating tether through space. Instead, we can simply cast a straight ray from our point out to infinity and add up the integer jumps whenever that ray crosses a path. The fragile ray casting rule we started with was not entirely wrong. It was just missing the directional signs. Continuous rotation and straight ray crossings are 2 sides of the exact same coin. Now, why does the GPU care about converting rotation into ray crossings? Because GPUs are massive parallel engines built to do millions of tiny calculations at once. Instead of tracing a curve sequentially step by step, a graphics processor assigns a separate thread to every single pixel on your screen. Each pixel simply casts its own horizontal ray to the right, counts the signed path crossings, and computes its own local winding number in complete independence. What felt like a continuous topological journey is transformed into millions of instantaneous parallel checks. Once every pixel knows its winding number, deciding which pixels to color comes down to a simple choice of fill rule. Under the standard non-zero rule, any pixel with a winding number other than 0 is filled with color. The central core of our star, with its count of +2, lights up brightly alongside the outer points. But in font design and vector tools, you will often encounter the even-odd rule, which colors a pixel only if its winding number is odd. Here, +2 is even, so the core stays empty. 2 different design choices, both powered by the exact same underlying integer count. This simple arithmetic gives modern GPUs their remarkable speed and crispness. At boundary edges, where a path cuts directly across a pixel, the GPU can evaluate a handful of sub-pixel sample points in parallel, using this exact same test. By averaging the resulting winding numbers, the pixel smoothly transitions between color and transparency. The result is perfectly smooth vector graphics rendered in a fraction of a millisecond, no matter how complex or self-intersecting the shape might be. So, an anchor tied to a tracer turns a fragile boundary question into a robust, parallel calculation that never gets confused. But this leaves us with a tantalizing puzzle. In 2 dimensions, our tether swept out angles around a point along a 1-dimensional path. What happens if we step into 3 dimensions, where boundaries are 2-dimensional surfaces in space? How does a GPU or a computer graphics engine determine if a point is inside a complex, self-intersecting three-dimensional object? That higher dimensional geometry is a story for next time. You can now see vector shapes not as fragile boundaries but as topological landscapes measured by the total rotation of a tether. The same elegant logic extends far beyond computer graphics to describe winding numbers in higher dimensional topology. If a smooth, closed curve wraps around a point twice, what is the fewest number of times it must cross itself?